So I've done my little rant on action at a distance, but actually you guys have all seen action at a distance all the time. You take it for granted. Is the Earth touching this mass right now? No. Did it exert a force on the mass right now? Yes. But it didn't touch it. Yes, it did. But it touched the mass with something invisible that you can't see. The same way I used the meter stick to move Alex, and the same, it touched the mass with its field. A gravitational field reflects the effect that a mass has on the space around it. So right now, any mass in outer space is sending out, like the invisible tentacles of an octopus, a gravitational field, and that field exists at all times. It's waiting. It's just sitting there. As soon as you put a mass in that field will exert a force pulling that mass inwards. This is how gravity works. Then Einstein came along and said that that field is actually the curvature of space and time. And so we can take it one step further with gravity, but for now we're just going to stop there, and we're going to say what masses do is they send out, like the invisible tentacles of an octopus in all directions, gravitational fields. Fill in the appropriate relationships. The force of universal gravity, well, that was big G, big M, little m, over r squared. One way to think about the gravitational field was as a ratio. So you can skip a line for a second. The gravitational field, which we symbolized with little g, is the gravitational force divided by the mass. It's the acceleration due to gravity. It's how many newtons of force each kilogram experiences. It's newtons per kilogram. From that right there, we said, oh, well, if mg equals big G, big M, little m over r squared, it also allowed us to give an equation definition of G as a gravity field. We said, well, it's big G, big M over r squared. Two ways to find gravitational field strength. This is the one we did in Physics 11 all the time, 9.8. This was the one that allowed us to say, hey, what's G on the moon? What's G on Mars? What's G on any planet? If I know its mass, if I know its radius, I can tell you its gravitational field strength. What are the units of gravitational field? Well, the units are going to be, I guess, newtons per kilogram, force divided by mass. Hopefully nothing new there. That's the gravitational field strength. That's what's pulling two masses together. We can calculate it. For example, we can find it two ways. I can find the gravitational field strength this far from the Earth's center. You'll notice they gave me a radius. I'm going to use the equation that has a radius in it. I'm going to use this version of gravitational field strength. Dustin, if I compare that with Part B says find the gravitational field strength, the gravity field, of a 10 kilogram mass it has a weight of 750 newtons. Dustin, notice here they gave me a mass and a force. Here I'll find the gravitational field strength by going force divided by mass. You okay with that? This one I can do in my head. It looks like it's 750 divided by 10. In your head, Dustin, what's 750 divided by 10? This planet has a gravitational field strength of 75 newtons per kilogram. Tells me that planet's probably larger and heavier than the Earth. In A, I would use big G, 6.67 times 10 to the negative 11. Big M, 5.98 times 10 to the 24th. I still remember those two numbers. I'll forget them by June, but they're still fresh in my brain. All over 8.38 times 10 to the 6th squared. I know the gravitational field strength right on the Earth's surface is 9.8. We're further out. It's going to be a little less than 9.8. I can tell you that. And if I crunch the numbers, hey, Spencer, have I got a surprise for you? I managed to revive my calculator. Yeah, I said slightly less than 9.8, 5.68 meters per second squared. Or newtons per kilogram. If you do the numbers, you'll find newtons per kilogram and meters per second squared are actually the same units. Meters per second squared is what we used in Physics 11 because usually we were talking about gravity as an acceleration. But if we want to go cosmic, you can start now to think about gravitational field as that which causes a force. It's not a force, it's not a newtons, it's the thing that's linking two objects together so that they can exert the force on each other. You okay with that, Jason? I've gone on a rant for a reason. Because it turns out not only is there gravitational fields, we have electrical fields. That's what's causing those charged objects to repel or attract without touching each other. They are touching each other. It's just they're touching each other with the invisible tentacles of an octopus that I can't see, called an electric field. So we're going to define an electric field almost the same way. We say that the electric field reflects the effect that a charge has on the space around it. So this charge is sending out, like the invisible tentacles of an octopus, in all directions, an electric field, which is sitting there waiting. As soon as a second charge, another charge, is placed in that field, there's going to be a force. I put the arrows pointing both ways because I don't know whether these are like or unlike. I don't know whether they repel or attract. Okay? Fill in the appropriate relationships. Okay. Well, the force of electricity is K, big Q, little q, over r squared. I'm writing it that way so it looks more like gravity. So big Q is the planetary charge sending out the field. Little q is the tiny charge that's stuck in the field. We said this. We said that electric field was equal to the force per coulomb. Force on each, the force per coulomb of charge. I'll show you what I mean. Stay here. The same way as we defined gravity field as the force per mass, electric field is defined as how many newtons of force on each coulomb of charge. As the ratio, if I want to write it as an equation, it's going to be Fe divided by little q. The symbol for electric field is E with a vector sign, not to be confused with energy. By the way, this is why I use PE and KE for energy, even though your formula sheet uses an E for energy, because we also use an E for electric field. Well, that can't be confusing. Yeah, it can. If I take this one step further, I would say electric field is the force per coulomb, per charge. It's the force on that little orbiting charge. So I stuck it on the bottom, and Clay, you might notice, hey, that happens. It does. And just like we had two ways to calculate gravitational field, big G, big M over R squared, or force over mass, turns out there's two ways to calculate electric field. Force over charge, that guy, or KQ over R squared. Mitchell, do you notice how this looks an awful lot like what we just wrote for gravity? By the way, that and the fact that Coulomb's law looks so much like the equation for gravity has led millions of physicists over the years to say, well, wait a minute. If in electricity we can have both attract and repel, if in electricity stuff can fall up, is there an anti-gravity particle out there? I mean, there's two types of charge. Isn't there two types of mass? Isn't there anti-mass? And I'm not talking antimatter. Isn't there negative mass? Some kind of a mass that instead of attracting each other, they would repel each other? We're looking. Because it sure does look like it mathematically. We haven't found it yet. That might be dark energy or dark matter, or we don't know yet, but we're looking. What are the units for electric field? Well, I guess newtons per coulomb. The units for coulomb is, you're right, capital C. Okay. The equation is a scalar equation, but I put a vector on E because we're going to have to define a direction. You see, unlike gravity, Clay, where stuff does always fall down, in electricity, like stuff can fall up. So we're going to have to maybe come up with some kind of a directional component here. With me so far? Also, turn the page. I should point out electric fields can't be negative. A negative answer simply indicates an attraction. Instead, much like our force equation, where you can imagine little absolute value signs around the charge, we're not going to put negatives and positives into the equation. We'll decide the direction afterwards. So there's two ways to find the electric field. What is example, Alex, what does example A want me to find?
Electric field.
Alex Fan, what does example B want me to find? Okay, you know what? There's two ways to find electric field. The first way to find electric field is if you know the big planetary charge that's causing the field, and you know how far away you are from that charge. And really what I look for is if they've given me a radius. The second way is if you know the force at that location and the small orbiting charge at that location. Both of these, by the way, I should point out, are on your formula sheet. But we're going to run into a problem. If I gave you one piece of advice for this unit, and I'm talking to almost all of you, do not put off the homework until the end and try and cram it. It'll be a disaster. I've seen it happen before. The reason is, if you look at the equations for this unit, we have F equals K Q1 Q2 over R squared. We have E equals K Q over R squared. We have EP equals K Q1 Q2 over R. We have V equals K Q over R. Mr. A lot alike. You think people get them mixed up? Yeah. And here's the problem, Kyle. If I ask you to find the electron, and instead you tell me the energy, I have to give you 0. I can't even give you part marks, because it's as though I said, could you please find the velocity, and for some reason you decided to find the momentum. I can't even give you any part marks. And that's the big risk here. So keep up with the homework. Example 4. You know what? They gave me a force they gave me a test charge or an orbital charge. Here, to find the electric field, I'm going to use force divided by little charge. Compare that with in B, Jason, they gave me a distance, and this is the charge that's causing the force. This is the big planetary charge. This is the charge that's causing the electric field. Here, it's going to be kq over r squared. The first one, it's going to be 5.2 times 10 to the negative 4, all divided by, am I going to put a negative in here? No. 0.5 microcoulombs times 10 to the negative 6. How big is the electric field that this charge is experiencing? That big, 1,040. You'll find most electric fields are in the thousands or in the tens of thousands, sometimes in the hundreds of thousands. If you get an electric field of 0.6, you've probably messed up. If you get an electric field of 1,000,000, you've probably messed up. 1,040 newtons per coulomb. Compare that with finding the electric field to the right of a charge. It's going to be 9 times 10 to the 9th. The charge is 2.3 micro times 10 to the negative 6 coulombs, all divided by 0.45 squared. How big is the electric field at that location? Uh, 102,000. Is that right? Double check me. Yeah. 102,000 newtons per coulomb. Like I said, most electric fields are in the thousands, tens of thousands, or hundreds of thousands. So that's how we can calculate it, but we're going to start to do a lot more with it. We have to talk about the direction of electric field. With gravity, this was never an issue because stuff falls down. It was always attract. It's always attract. But electricity has this notion, Vikas, that like,
repel.
Unlike,
Attract.
We got two directions. So we have to define the direction, and here's how we define it. You want to underline and memorize this. The electric field direction is defined as the direction a small positive charge would go if it was placed at that point. The short version is which way positive would go if it could. But Jason, it's a small positive test charge. How small? So small it doesn't have its own electric field, because that would change the question, which really, Clay, technically means it's an imaginary test charge. But you know what? You just say, which way would a positive at that location want to move if it could? That's the direction of the electric field at that location. A says, find the direction of the electric field at the point where a negative charge experiences a force towards the south. Which way is this negative charge experiencing a force? Toward the? Which way would a positive experience a force then? Keep it simple. If a negative feels the force to the south, which way will a positive feel a force? Which way a positive would want to move if it could. If a negative is moving south, a positive is going to move north. Why? We had to define it some way, Jason, and this is the convention we came up with. Why do we have to define it? Because stuff can fall up. So unlike gravity, we have to be careful with direction. B, so what would the electric field be right there? Well, first, we have to look at big Q, which is causing it. It tells me that big Q has a charge of positive 2.3 microcoulombs. So if you look at that location X, which way would a tiny positive right there want to move if it could? We're going to use the notion of like repel and unlike attract. So if you put a little positive right where that X is, would it be attracted or repelled? Repelled. Put your pencils down, look up. See if this will run. Have to, I think, pause the video though. Behold the electric field of dreams. I've just added a charge. The arrows point in the direction of the electric field. That charge, is it negative or positive? Figure it out. Negative. Why? Because arrows point which way a positive would want to move if it could. Pointing towards it must mean it must be negative because a positive would want to move towards it. See it? If I add another charge, both of these charges are like charges. Because what will like charges do? See, they're repelling each other. And you can see how their overlapping fields are changing. This is going on, by the way, Clay, at an atomic, at a subatomic level all the time with protons and electrons, and all this is going on. You just don't notice it. You know what? Let's add another charge, but this time, let's add a positive one. Okay, we have all this interaction going on. This charge right here, positive or negative? Because a positive would want to move towards it. What about here? A little tougher to tell. Let's move this guy here. This charge right here, positive or negative? Positive. Okay. This is the usefulness of the arrows. In fact, a lot of what we're going to do are electric field diagrams. Part C says, draw the electric field around a positive charge. Okay. Well, first of all, I would probably draw some lines like this. I might draw 8 lines. I'm going to put arrows on those lines. Am I going to put the arrows pointing towards the positive or pointing away from the positive? There you go. Michael Faraday was one of the ones who gave us these electric field diagrams, Travis. And here's how they work. The number of lines tells you how strong, how big the charge is. In other words, if I had another charge with 16 lines, it's twice as big as this one. If I have another charge with 4 lines, it's half as big as this one. And how close the lines are tell you how strong the field is. Here, the lines are closer together, stronger field. Here, the lines are further apart, weaker field. Okay. In other words, the further you go from the charge, the weaker the field, but you can also show it graphically or representationally. This distance is fairly small. You know what? Stronger field, weaker field, weaker field. Or we can represent them like this. See if this one runs a little faster. Hey, it did. In theory, here we go. Agree and continue. So I'm going to move a positive charge out right there, and I'm going to show you the electric field. Okay. This sim, instead of having the arrows get further and closer together, has them get lighter as the electric field gets weaker and weaker and weaker. So this would be the electric field of a single positive charge. I can bring an electric field sensor. It's really strong right there. As I go further away, it gets weaker and weaker and weaker and weaker and weaker until it's basically non-existent. The closer I get to it, the stronger the field, and it's always, in this case, which way would a positive want to move if it could? Repel. As opposed to now the electric field points towards it. What if we had more than one charge? Well, that's a good question. Well, first of all, if I wanted to draw the electric field around a negative charge, this time I'm only going to do 4 lines. Because I only did 4 lines, Jason, I'd be telling you that this charge is half as big as the one in part C, and the electric field arrows will point towards, will point towards, will point towards. Good question. Why is there a plus sign? It's not supposed to be a plus sign. Scribble that out. Thank you. Because I was cutting and pasting diagrams and I just noticed that. Oops. Electric field of dreams I already showed you. So what's the direction of an electric field? Here is the long version. We ask, which way would a positive want to move if it could? The short version is from positive to negative. I don't like that one, even though it's the short version, because sometimes you might only have one charge in your picture, and so you, from positive to negative, there's no negative in my picture. I always just say, which way would a positive want to move if it could? And that will handle it if there's a single negative charge, if there's a single positive charge, or if there's multiple charges. To determine the electric field of 2 charges, the principle of superposition states that we do one at a time and we add them vectorially. The same way as if we wanted to find the force from 3 charges, we did 2 at a time and added them vectorially. I like example 6. I like example 6 is going to be on your test as a written question. You're going to be asked to find the electric field of 2 overlapping charges, the net field. So, find the electric field and direction at the indicated point right there. I'm going to call this charge 1. I'm going to call this charge 2. They gave me, I'm going to use the electric field equation that has R in it. KQ over R squared. Common mistakes that I see, I give kids this question and they find the force. They go F equals K, Q1, Q2 over R squared. And I want the force, and unfortunately I have to give you a 0. I want the net electric field at that location. Okay, I'm going to find, Dustin, the electric field from charge 1. That's going to be K charge 1 over R1 squared. Then I'm going to find the electric field from charge 2, which is going to be K Q2 over R2 squared. But for both of these, Manny, I'm going to find both magnitude and direction, because I'm going to have to add them vectorially. I'm not going to have to go tip to tail, because they're in a nice straight line. I'm going to be able to go winner minus loser. Or if they're in the same direction, winner plus winner. What's K? 9 times 10 to the 9th. Charge 1 is 1 microcoulomb. R1 squared is 1 squared. Really, Dale? You're using a calculator? Isn't dividing by 1 squared just not going to change it? Isn't this really 9 times 1, which is what? 9. And then 10 to the 9th times 10 to the negative 6. You can check me, but I'm pretty sure the answer, isn't it a 9 with 3 extra zeros kicking around? 9,000? Which works because I told you most electric fields are in the thousands, tens of thousands, or hundreds of thousands. So at least I know I think I'm right. newtons per coulomb. Direction. So, sitting right here, which way would a positive want to move if it could because of this guy? Give you a hint. To the right or to the left? It's attract or repel. I think it's repel to the right. Yes? So let's add our direction to the right. Nine times 10 to the ninth. Also 1 times 10 to the negative 6, 1 microcoulomb. All over. Careful, not 4 squared. How far is it from here to here? Clay. 3 squared. Dale's not going to reach for his calculator. He's going to cleverly notice, what's 3 squared?
9.
Which will cancel out that 9 in the top, and really I have 1 times 10 to the 9th times 10 to the negative 6. I think it's going to be a 1. It's really 10 to the 9th times 10 to the negative 6. You can add the exponents. I think you're just going to get 1,000. Yes? Newtons per coulomb. Direction. Which way would a positive want to move because of that guy? Left. Oh! I'm so used to that touch screen not being turned on. I'm so used to being able to wipe dust off without... God. Hey, what do you think 9,000 right plus 1,000 left is? That's the principle of superposition. Kyle, it's a fancy phrase for saying you do them one at a time. Or if it's forces, because forces require 2 charges, you do them 2 at a time. But you can't do it all at once. I like that question. Did I say that already? Good. Draw approximately the resultant electric field at the indicated field points. You know what? I'm going to save the top 2 for last because those are yucky. I'm going to do the ones that are in a nice straight line. And in fact, I think in one location, the electric field is 0. I think dead center, because which way would a positive want to move if it could? In either direction, and I think both charges are the same. Oh yeah, it says both charges are 1 microcoulomb, so the electric field right dead center is 0. What about right here? Don't put an arrow on yours, but just we'll focus on that one. Well, which way is this charge exerting an electric field right there? To the left or to the right? To the right. Which way is this charge exerting an electric field right there? To the left or to the right? Which one's bigger? Because it's closer. In other words, you can think about it, Manny, as electric field this way, electric field that way. You know what? Your net electric field is that way. Is that okay? What about this charge here? I think that way. In fact, I think you could make an argument, you know what? I can simulate this. Let's get rid of the negative. Let's get rid of the sensor. Let's put 2 positive charges out there. And I'm going to turn the electric field lines off. I think what happens is, right here, the electric field is really strong to the left. As I go further and further and further and further and further, it gets weaker. There's that 0 point dead center. And now the electric field gets stronger and stronger and stronger and stronger and stronger and stronger to the right. Is that okay? Let's do the trickier ones. Right here. Which way is the electric field from this guy right there? Which way would a positive want to move right there because of this charge? Straight up. Which way would a positive want to move because of this guy? I think diagonally a little up and a little bit left, but not as strong because it's further away. In fact, I think I could add these two fields together tip to tail. I think the net electric field is probably kind of like that, almost straight up, but not quite, a little bit to the left. Let's find out. Almost straight up, but not quite, a little bit to the left. That is a little bit tilted, isn't it? What do you think right here? What do you think right here? I think the left-hand charge is pushing that way. Yes? I think the right-hand charge is pushing that way. Hey, are those two at angles to each other? Are they vectors? How might I add them together? I think I'm going to get that plus that. I think the resultant is going to be straight up because the pushing sideways are going to cancel each other out. Let's see. Yep. Okay. Draw the electric field pattern for equal like charges. Because like. Okay. And are these positives or negatives? So my arrows are going to be pointing away from them. This is kind of a complicated idea, but it's going to look something like this. An electric field line will start out going this way and it'll get repelled. It'll start out going this way, it'll get repelled. And you'll notice that gives us pointing straight up at that location that we said was pointing straight up. Electric field line this way will start out going like this, start out going like this and get repelled. Start out going like this, start out going like that, start out going like this, start out going like that. Kind of like that. It's tough to visualize. I'll bring the sim on in a second, but kind of like that. Remember I said to you with electric field lines, the closer they are, the stronger the field. So I notice my lines came together fairly, are getting closer and closer as I move up. I think that means that as I move up, the field should get stronger and stronger. As I move down, the field should get weaker. As I move up, the field should get stronger. Okay, it is. It is. Well, sort of like, it's tough to visualize, but sort of like that. You know what? I find these tricky to draw, but I think I have a nice picture here. Yeah, here is two positives right here. Here is two unlike charges, and here is a positive and a negative. So equal and opposite charges. Here's what I do know. If they're unlike, there would be one line pointing zoom straight like that, because a positive would both move away from the positive and towards the negative. A line would curve kind of like that, because it'd be attracted towards. It would be repelled and attracted towards. It would be repelled and attracted towards. It would be repelled and attracted towards. I'll stop there. 4 lines on each tells me that each charge is the same size, the same way as 6 lines on each of these tells me those charges are the same size. I'm not saying it's 6 coulombs. I'm just saying you could say they must be the same size. But I struggle to draw these. The idea of an electric field originated with Michael Faraday, one of my nerd heroes. I will go on a Faraday rant, but not today. He used lines of force, these electric field diagrams, because he was uneducated and had very little math background. But he said, I can draw a picture. It's which way a positive would tend to move if it was placed anywhere in the field. So here I stole these from the internet, are 4 lovely little examples. And I've showed you the sim, the FET charges and fields. So summary. We can find electric field 2 ways. We can find it using the definition, the fact that it's how many newtons per coulomb of force. Sorry, how many newtons per coulomb of electric field, the force per coulomb. We can find it by saying, oh, you told me the force at that location, you told me the charge at that location, that must be the electric field at that location. Or, Max, if you tell me the big charge Q that's creating the field, I can find the electric field by using the point charge equation. Here's the planetary charge. And I'm calling it a planet. I know it's not in mass, but the big charge that's causing the electric field. Here's the charge that's, I'll say, sort of like it's in orbit, sitting by itself. The little tiny charge. Direction is found by which way would a positive test charge want to move if it could. It's away from positive towards a negative. Forces, we now have 2 ways to find it. It can be found using Coulomb's law. The electric force is K Q1 Q2 over R squared. That was last day, Nick. But Nick, is there a force in this equation here? Get the F by itself. How to get the F by itself? What would I do with this Q? Another way to find electric force is a charge at that location times the electric field at that location. If you happen to know those, it's way faster. Direction of electric force is found by considering whether charges attract or repel. It's really found by using like, repel, unlike, attract. So we don't put pluses or minuses into the equations. We don't put positives or negative charges in the equations. We decide the direction. Oh, and since they're vectors, if we have several charges, we need to add them vectorially. This brings us to the most addictive bonus video game ever. I warn you. First of all, your homework. Try number 1. Try number 4. Nope, you know what? Number 5. Please notice that your distance in number 5 is micrometers. They didn't tell you the charge. It's an electron. You should know the charge. What's the charge on an electron? 1.6 times 10 to negative 19. We don't include the negative in these equations. Okay. Find the resultant field between positive and negative 1 microcoulombs. I haven't done this yet, so it says find the net force given the electric field. You'll use that second version of force. Oh, then it says find its speed. I think you can find its acceleration and then find its speed, because they gave you the mass. $11. $13. I'm going to give you 15. 15 is, you're going to have to add those 2 electric fields tip to tail and do some trig, but it's going to be Pythagoras. I'm not going to give you 16. 16 is not a nice right angle triangle. It's yucky, so I'm going to pass that. 17. And this brings us to the addictive video game, but I'll pause the video.